Good morning, everybody. So, we'll still with the tungsten enzymes, because we have started one important thing on tungsten is the corresponding model compounds and how these model compounds can help us in understanding the actual reaction based on the metal center, what is taking place in all these tungsten containing enzymes. So, one important aspect what we have discovered so far related to all these tungsten bearing synthetic molecules as well as the metalloenzymes are that these are responsible for typical electron transfer reactions. So, when these electron transfer reactions are taking place and we are just simply changing the corresponding oxidation states on the tungsten and how the corresponding ligand system, which is sulfur based, and the tungsto-terene unit where we have two negative charges on the thiol backbone. And in stabilizing this high oxidation state, when we can consider that tungsten is present in +6 oxidation state, which is the most known one, where the highest possible oxidation state of tungsten is residing, and the effective charge transfer from the sulfur, which is bigger, because this amount of charge transfer from sulfur anions, the thiolate anions, would be definitely bigger than the corresponding transfer from the oxygen atoms. So, we can just simply compare the donor ability of sulfur versus oxygen in these systems. So, one very important thing what we can study is that whatever model compound we make on these two ligands, say based on tungsten, which can lead us to some information whether we should be able to oxidize this tungsten center if this center is present in the lower oxidation state, that means the tetravalent state. So, if we have the tetravalent state, and if we go for the corresponding oxidation to pentavalent state and the hexavalent state, and if we can measure the corresponding E0 values of these two steps, that means how easily and how quickly we can oxidize the tungsten center from the tetravalent state to pentavalent to hexavalent state. So, if we just compare these E0 values and if we can compare these, that means if these values for one particular type of molecules are E1 and another type is E2, then by simply comparing these two values, either E1 can be less than E2 or E1 can be greater than E2. These are the two situations. We cannot have any situation where E1 is equal to E2. So, the effective charge transfer from the sulfur bearing ligands we can compare with that of the charge transfer from the oxygen bearing ligands. So, if we find that this particular oxidation potential E0 value for oxidation is less than that of for the corresponding species surrounded by the oxygen bearing ligand, we can simply say that the compound in sulfur environment can be easily oxidized compared to those in oxygen environment. So, if we take the corresponding oxidizing agent, because for this sort of electron transfer based on this thing, that means this is the reduction, and on the other hand if we can have the oxidation on the tetravalent state like this, we need some oxidizing agent. So, this oxidizing agent will immediately tell us, because all the known oxidizing agents, that means the corresponding redox potential value E0 values for all the different oxidizing agents starting from chlorine gas, oxygen gas and all other things. So, how we can choose the corresponding oxidizing agent? By knowing the corresponding E1 values or E10 or E20 values for the corresponding tungsten compound can tell us how easily we can oxidize this center to the corresponding pentavalent state or the hexavalent state. So, one such situation we have encountered, the example we have taken the last time, that one is the malonitrile dithiol based ligand we have taken. This is basically what we have seen, that this is basically sulfur bearing ligand. So, dithiol in type of ligand, you have the backbone with a double bond and 2 sulfur in the negative charge. So, this malonitrile dithiol type of ligand, when it is stabilizing the tungsten and when you have the corresponding tetravalent state. So, this one, so we just take the system on this malonitrile dithiol. These are the CN groups. So, you have 2 ligands and we have the tungsten, and depending upon the starting metallic salt what we have used for the preparation of this compound, if we get this as the corresponding only monoxo species, which is in a typical square pyramidal geometry. So, this geometry, so this is the basic square plane, and we have the square pyramidal geometry, and 4 of these sulfur anions providing 4 negative charge, and this oxygen is also providing 2 negative charge. So, 4 plus 2, 6 negative charges are there, and tungsten in +4 oxidation state will give us an overall 2 negative charge on the complex anion. So, it can be stabilized by the corresponding ammonium salt, which is tetraethyl ammonium salt. So, the question is that how we get this particular one in the +4 oxidation state. So, that means the stabilization of the species of the model compound in low oxidation state. So, in this low oxidation state, it can be achieved if we have a corresponding monoxo compound. The compound is therefore the simple monoxo compound. So, if we take this compound, that means in the +4 oxidation state, the monoxo malonitrile dithiolate compound of tungsten, which is soluble in dichloromethane. The solvent is dichloromethane, and to exclude the presence of air, that means we do not want to take any chance that air is the oxidizing agent, and following oxidation by air, the oxidized species can also be different and it can transfer oxygen. We just remove the oxygen present by argon environment. So, under argon environment, it reacts basically with one equivalent of mercury chloride. So, some idea from the corresponding E0 value of mercury chloride. So, that mercury chloride, what I told last day, that if we are utilizing mercury chloride as our oxidizing agent, it has several advantages, like the way we use mercury chloride solutions in analytical chemistry. So, what we did there in analytical chemistry, this mercury chloride is a very useful reagent for oxidizing any particular one, that means any center which can be Fe2 plus. So, this can be oxidized by this mercury chloride. So, for this ferrous ion or any other one, this mercury chloride can be a very good oxidizing agent. So, this particular one, because this mercury chloride do settle between its other reduced form, which is mercurous chloride. So, when mercurous chloride is forming, it has less solubility even in some organic solvent medium, which is less soluble in aqueous medium. So, it is less soluble in aqueous medium. So, mercurous chloride immediately precipitates out from there. So, when we use this mercury chloride from there, the color of the solution immediately changes from pink to some EPR inactive light reddish brown solution. So, the color change is there. So, one is there when we have this corresponding compound, that means this one which is formed immediately. So, due to the color change, nothing is happening which can be sensed by EPR spectral measurement. So, EPR is a very sensitive instrument for measuring the corresponding spectrum, where we can measure the spectrum by knowing that whether there is any change in oxidation state on the tungsten. So, if the tungsten center goes from +4 to +5, then only we can detect the presence of tungsten 5. That means the pentavalent state of tungsten in the medium, by knowing the corresponding spectrum, the corresponding EPR spectrum of the species in solution. But what is happening there, that the color change is taking place from pink to reddish brown solution. So, pink was not EPR active, reddish brown solution was also not EPR active. But what happens at the same time, after some time, mercurous chloride gets precipitated and the solution then started displaying one EPR signal at G is equal to 1.893. So, these are very characteristic values depending upon the corresponding magnetic field. So, if we have the magnetic field and the corresponding absorption is taking place like this, so this is the typical EPR spectrum for that solution, and we basically measure the corresponding G value. How we measure this corresponding G value at 1.893 is that how much this particular one, that means this is the corresponding field, that means the magnetic field, this 3200 Gauss for diphenyl picaryl hydrazine radical. So, diphenyl picaryl hydrazine radical shows corresponding signal at around 3200 Gauss, and with respect to that value where this particular one is appearing. So, compared to this, because this field is known and this corresponding G value 2.0034 is also known. So, based on that value on DPPH, we can determine the corresponding G value for this signal. This is a very simple technique. So, by simply comparing with the reference material, the reference sample for EPR spectrum. For reference sample is the corresponding DPPH, and with respect to DPPH we find out the field, and from the field we can calculate the corresponding G value, which is therefore characteristic for the species based on tungsten 5. So, how this tungsten 5 is forming in the solution? What we have done? We have done the reaction of the tetravalent malonitrile diethyl compound of tungsten with mercury chloride. So, immediately what is happening there, this particular mercury chloride is transferring one of its chloride ion to the tungsten site, which is very important, and this one basically. So, you have this tungsten site as we have these two ligand groups attached to the tungsten, and then we have this oxo species 1, and we have the transfer of this Cl and loosely bound HgCl is there. So, this particular one, so HgCl, so transferring one chloride ion, this mercury is in +2 oxidation state, but this mercury is in +1 oxidation state. So, if the electron transfer is taking place to the mercury, it can be reduced to mercurial species. So, when chloride is transferring, so one more electron transfer is taking place, that means this tungsten site which was in the +4. So, it is 4 plus, it can go simply to 5 plus, that means one electron it can transfer to the mercury site. So, mercury center which was in the +2 oxidation state will be reduced to +1, and this can dimerize. So, this HgCl will dimerize. So, dimerization can take place. Therefore, that dimerization will lead to the formation of Hg2Cl2. So, thing is that when this reddish brown solution is forming, so this particular species, when mercurious chloride is still attached to the tungsten site, and this particular one basically when we consider that is because this immediate formation of this tungsten which is in the +6 oxidation state. So, that means if we just go for this to +6 also, which is a 2 electron transfer process. So, this is going for +5, still we have one charge which is taken care of by this particular mercurious chloride species derived from the mercury chloride. So, due to that basically, so electron transfer will now take place over here. So, this is tungsten 6 and this is the corresponding mercury center. So, if the electron transfer is now taking place, because this is still mercury chloride, that means HgCl plus, this is one positive charge is there still. So, due to that electron transfer, this one go for dimerization and mercurious chloride is getting precipitated from the system, and we will end up with something where we have the tungsten center is again reduced back to a pentavalent state. So, this is an unique example for stabilizing the tungsten in the +5 oxidation state by using a very simple reagent which is nothing but mercury chloride. So, mercury chloride is basically responsible for oxidation of this tungsten compound in +4 oxidation state to tungsten 5 through some intermediate which is tungsten 6, when HgCl is attached to this tungsten 6 and whose color was reddish brown. And since the starting tetravalent as well as this intermediate hexavalent, both of them are EPR inactive, we do not get any EPR signal for the pink solution as well as for this reddish brown solution. But what we get when after the precipitation of mercurous chloride, the solution gets turbid and we can filter it out and the turbidity goes away, and the clear solution, if we can take for again the EPR spectral measurement, we find the same signal which was earlier we are finding after the precipitation of mercurous chloride in the reaction medium, that this particular species is definitely responsible for the corresponding EPR spectrum in +5 oxidation state. So, what is happening there basically when we have in case of the monoxo species, we have one oxo site, one oxo center on the tungsten, but during this particular one when we go for this particular oxidation. So, what is happening therefore that tungsten center with two ligands, we have a double bond O and one Cl. So, this is some kind of again something we all know as the corresponding oxidation of the center and one more ligand addition, because this is when we have this monoxo one, this monoxo compound was pentacoordinated, and when we go for oxidation plus addition of one ligand, this is the new ligand which has come to attach to the tungsten side, and the system goes from pentacoordinated one to a hexacoordinated system. With the addition of chloride anion as a new ligand. So, what we find that as we go for the lower oxidation state for tungsten in the tetravalent one, we have here basically low coordination number for the 4 plus, but when we take out the electron, we oxidize the center through pentavalent to hexavalent, the electron demand for the +6 oxidation state has changed, and it is more electron greedy through the donation of the new ligands. So, we have at this situation we have the corresponding possible high coordination number for an hexacoordinated species. So, it is very simple, we can consider we can go for oxidation as well as addition of new ligand, which something we call in case of catalysis, that is the oxidative addition reaction. So, we go for the corresponding oxidation, we allow the corresponding expansion of coordination number, and then we introduce the corresponding chloride anion over there. So, this particular chloride transfer from mercury chloride is a very simple and very unique reaction, where we change the oxidation state as well as we expand the coordination number around this tungsten ion. So, this is a very useful and effective information for the catalysis. So, what is happening there, that means if we just consider some other model compounds where we just simply want to have a reaction, because this sort of diethylene ligands are well known. So, this sort of this again this diethylene type of ligand. So, these are S minus and S minus ligand. So, these are very simple also if we have the corresponding quinoxalene diethyl type of ligand. So, quinoxalene diethyl, if we have a quinoxalene backbone, this is also a very simple reaction for that. So, quinoxalene diethyl, so this is SS type of ligand, and it gives very useful compound with nickel. So, nickel when reacts with this sort of ligand gives a bischelate, and that bischelate is basically a square planar one. So, when we have this particular, sometimes we can generate this diethyl ligand in situ in solution, the reactive species which is giving rise to this particular quinoxalene diethyl type of thing is also used for making the corresponding template reaction for nickel. So, NiL2 compound which can be very easily make. Now, the metal ion metathesis reaction, that means we substitute this particular, that means nickel will be substituted by tungsten. So, hoping that in that particular environment when these two sulfur ligands are there, so nickel will be simply replaced by the tungsten and we immediately get the corresponding species as tungsten with these two ligands which were originally attached to the nickel side. But we can also go for using a corresponding carbonyl compound of tungsten, because like molybdenum, like chromium, tungsten also gives rise to very useful carbonyl compounds, including the tungsten hexacarbonyl species, where tungsten is surrounded by 6 carbon monoxide molecules. And one such intermediate species is there which is stabilized by 3 acetonitrile ligands as well as 3 carbon monoxide ligands to stabilize a tungsten in hexacoordinated form, and in same dichloromethane solvent, which is a very useful solvent for reactions of this type of model compounds, we react with this particular nickel compound where R can be methyl-methyl or phenyl-phenyl diethylene type of ligand. So, what is happening there, that the loosely bound acetonitrile molecules which is basically present over there. So, these loosely bound acetonitrile molecules, so all three acetonitrile solvent molecules, acetonitrile is a very useful solvent molecule also. So, all three acetonitrile as well as one carbon monoxide molecule goes away, giving rise to one particular highly distorted type of hexacoordinated species for tungsten, where we have 2 carbonyl molecules still attached to this particular tungsten species. So, what we basically find there, that whenever we get this, that means this was basically tungsten in the zero oxidation state, which undergoes oxidation as we remove this particular carbonyl as well as the acetonitrile molecules, and we have the corresponding stabilization from the sulfur units. So, these sulfur units basically go for the stabilization for the tungsten charge on it, and we get a simple compound of that where we have the basic core, the metalloenzyme type, tungstoenzyme type of basic core bound to 4 sulfur groups. This was basically our idea. Wherever we make this molecule, which should be the model compound of the tungsten enzyme, we have these 4 groups which should be bound to 4 sulfur atoms. So, when these 4 sulfur groups are bound to this tungsten, we have 2 carbonyl functions. So, how these carbonyl functions, that means these are there for our catalytically active sites. So, wherever we go for these type of reactions on the model compounds, we see that these are the corresponding active sites. So, on tungsten we have 2 other positions which are nothing but our active sites for catalytic reactions. So, these 2 sites are very important to have. So, through these reactions with tungsten carbonyl starting material, we have 2 carbonyl groups on these 2 positions. So, next we can see the corresponding reactivity pattern, how these 2 carbonyl groups, when they are bound to 4 sulfur bearing ligands, how they are reacting with different reagents, which can give us some idea that whether we can retain some of these carbonyl functions or we can just completely remove these carbonyl groups. That means, whether these carbon dioxide monoxide ligands can be retained there or can be kicked out. So, the same tungsten when react with tetraethyl ammonium hydroxide. So, when it is reacting with simple base, this is a very strong base though compared to sodium hydroxide or potassium hydroxide. The tetraethyl ammonium ion based base, the tetraethyl ammonium hydroxide, immediately provides the corresponding OH minus group to this tungsten site, and it immediately cleaves these two carbonyl groups. The carbon monoxide molecules are going away from tungsten and a double bond is forming there between oxygen and tungsten. So, what is happening there when we provide this HO minus as the corresponding salt of tetraethyl ammonium ion to the tungsten site. So, these two tungsten site was attached to those two carbonyl functions. So, this can go and occupy that particular position, and during that occupancy intermediate state is forming where tungsten is coordinating with the hydroxide anion. So, WOH is forming from that side, and which then in the next step go for deprotonation, and that deprotonation would lead to the tungsten oxygen double bond species. So, we get this particular tungsten double bond O species, and the corresponding oxidation state is also not changing much. We have 2 negative charge on it because this 4 sulfur is providing 4 negative charge and oxygen is providing 2 negative charge. Altogether we have 6 negative charge, which is balanced by the tetravalent tungsten, giving rise to an overall anionic charge 2 minus on the anionic complex of tungsten. So, this is one sort of reactivity with respect to a strong base. But if we go for the reactions with alkoxide ion instead of hydroxide ion, so if we use the corresponding salts of phenol or the corresponding salt of isopropyl alcohol, so isopropyl alcohol just simply go and bind to this particular tungsten site as the corresponding alkoxide group. Since this is sterically crowded, it will not allow to go for or attaching the corresponding 6th position because the starting compound is hexa coordinated, but the resulting compound is penta coordinated with the removal of both the two carbon monoxide molecules with the introduction or with the attachment of this alkoxide anion. So, way the hydroxide anion is reacting, which is giving rise to double bond tungsten species which is 5 coordinated, and still if we can have a single bonded tungsten oxygen bond to that of our alkoxide group, we still get a pentacoordinated species which is similar to that of the species number 36. So, both 36 and 39 are almost similar type of species forming over there, but in case of sulfur the reactivity is little bit different. If we just simply thiophenol anion or selenoanion corresponding PHS or PHSE minus species, which we get, this is SH is thiophenol and ACH is the corresponding selenophenol ACH. When both of them are anion, so the sulfur, the reactivity of the sulfur bearing incoming nucleophiles, how they are reacting with this dicarbonyl compound 35 can be tested. But interestingly, the course of the reaction is little bit different to that of our reaction with hydroxide ion or the alkoxide ion, is that one carbon monoxide can be retained with the introduction of one thiophenol unit by the replacement of the first carbon monoxide molecule. So, the product is still hexa coordinated where one carbon monoxide molecule is still present and the tungsten in a S5 environment. So, this is highly sulfur dominating environment where 5 sulfur groups are present around tungsten, and in that situation tungsten can still maintain its bond with that of a carbon monoxide molecule. So, charge transfer is such that this particular sulfur is unlike this one, it is not removing the corresponding carbon monoxide molecule from the tungsten. So, the reactivity pattern, so how the catalytic cycle is going on, that can be tested if we just simply go for the corresponding reactions with hydroxide ion, alkoxide ion or the thiophenol anion. In one more example, and the corresponding reaction system can be tested on this, that means when we have the dioxo molecules or monoxo molecules, that means when we have that corresponding species as 36 which is forming from 35 by the reaction with tetraethyl ammonium hydroxide. So, how this species, that means again it is like that of our enzyme type monoxo species. So, this how this monoxo species can be reacted, because this particular one is in the tetravalent state. So, the way we just now seen that how the corresponding compound, the model compound in tetravalent state can react with mercury chloride. So, we have done this one for testing the corresponding reaction of this 36 with that of iodine instead of corresponding oxidation with chlorine or any other mercury chloride type of thing. We just can go for simply iodine oxidation, and this iodine oxidation, this is basically the 36 compound is in the +4 oxidation state, and which is simply going for one electron oxidation only, giving rise to the corresponding tungsten compound in the pentavalent state. So, it will have one less negative charge on the anionic part of the compound. So, 37 is therefore the corresponding pentavalent compound. So, this 37 is bearing tungsten in the pentavalent state. So, it would be therefore EPR active. So, just by simply doing this reaction, that means we should be able to oxidize some of these compounds, particularly the biological compounds, the enzymes, the tungsten enzymes. We can go for the corresponding oxidation of this tungsten 4 plus to tungsten 5 plus by simple oxidation with iodine. So, iodine oxidation can be available because we know that the corresponding E0 value of the tungsten is close to plus 0.52 volt. So, it is a very low potential oxidizing agent compared to chlorine or bromine. So, this low potential oxidizing agent is also suitable for oxidizing tungsten from +4 oxidation state to +5 oxidation state. So, we see that in this particular case what we have utilized is a very mild oxidizing agent. So, this oxidizing agent is a mild one, and we should be able to generate one particular EPR active species. That means, this particular cycle of reactions most of the time goes through the pentavalent oxidizing state of tungsten. And one more reaction, this is the corresponding redox transfer reaction on the left. So, the change from 36 to 37 is basically the corresponding electron transfer reaction, whether we should be able to oxidize this tungsten site from tetravalent to the pentavalent state. And on the right what we get, that the conversion of 36 to 38 with the use of some oxo transfer reagent, which is trimethyl amine N-oxide. So, Me3N is well known to us, is a trimethyl amine species, and which is reacting with hydrogen peroxide or any other oxygen donor reagent to give trimethyl amine N oxide. The way we get pyridine with reaction with hydrogen peroxide can give pyridine N oxide. So, these N oxide molecules are very useful reagent for oxotransfer. So, they are useful reagents for oxotransfer reactions. So, we can transfer these oxygen atoms very nicely to any other system, which is well known for any study, because we all know that the formation of these oxo groups are very useful in catalysis, in any other industrial catalysis as well as biological catalysis. If we have any metal center and if we see that some substrate is reacting over there, and that particular substrate, if we see that this particular substrate has a double bond, and if we just manipulate on some reagent which is an oxotransfer reagent, whether we should be able to go for the corresponding epoxide formation. That means, the metal center is there, that is of well known Jacobson's catalyst based on manganese, and there one more useful reagent is that simple inorganic compound sodium hypochlorite. So, if sodium hypochlorite is given, and in this Jacobson's catalyst, is a silent type of ligand, that means these 4 positions are blocked, and initially the manganese compound what is forming is basically Mn, metal is Mn, and we have initially the manganese in the trivalent oxidation state is a 5 coordinated one, and through the reaction with NaOCl it basically gives a manganese which is not very stable, but in +5 oxidation state. So, that particular catalytically active species is responsible for the transfer of this oxygen to this alkene compound. So, it can be styrene or it can be any other compound bearing double bond, which can be very easily go for the corresponding epoxide formation. So, the epoxidation reaction is this epoxide reaction is basically catalyzing through this oxotransfer reagent. So, these basically all reagents are known as the corresponding good oxotransfer reagents, and if we can go for this any oxotransfer reaction on this particular tungsten model compound number 36, what will happen? Whether this particular tungsten site can accommodate further oxo group, that means we know that the tungsten center can go for like molybdenum, that both monoxo species as well as dioxo species. So, in this particular one only there is a change in orientation of the corresponding positioning of these ligands. So, we have a roughly square pyramidal 5 coordinated tungsten compound in the tetravalent state, and through the simple transfer of this oxide anion, this oxotransfer reaction from trimethyl amine N oxide reagent, just simply go for the corresponding hexa coordinated compound, and tungsten goes from +4 to +6 oxidation state, and these two oxo groups basically take the positions, they are cis dioxo compounds. So, these two oxygen positions are cis. is not that this oxygen will go and attack this tungsten from the opposite side of the existing tungsten oxygen bond. So, instead of that, the reorganization of this bidentate ligand. So, this bidentate ligand is basically pushed from this side to that side, and this oxo group is attacking from there. So, when the oxo group is attacking the tungsten side from this side, these two ligands are basically pushed down, and one of the sulfur position is taking the corresponding trans position with that of the existing oxygen atom, and we get some reorganized form, that means the hexa coordinated species as the corresponding hexavalent compound. So, what we get if we have a catalytically active or the catalytically proactive species on tungsten base, which is the compound number 36, we can go for the electron transfer, and what is happening after simple electron transfer and what is happening after electron transfer followed by ligand transfer also, and which is some other kind of oxidative addition reaction which is different from that we have seen just now for the chloride. In case of Cl minus, the oxidation state was changing from +4 to +5, but in this particular case due to oxo transfer, the oxidation state on tungsten is changing from +4 to +6. So, these reactions also can be examined for the other compound which was 40, that means when the phenoxide ion like that of alkoxide anion, which is pentacoordinated one, is reacting with that of our other reagents. So, when this basically like that of trimethyl amine N oxide reaction. So, for the trimethyl amine N oxide reaction, it goes to these two positions. Similarly, when this trimethyl amine N oxide is reacting with compound number 40, what is happening there, that this particular one can nicely accommodate the oxo group, and this oxo group is now will straightaway forming the corresponding species what was present from this oxo compound. So, this is basically the compound number 40 is our non-oxo compound, and this non-oxo compound is basically reacting with some oxo source or some oxo transfer reagent, immediately forming the oxo compound, and this is again an hexacoordinated compound, but made of one oxo, one phenoxo. So, oxido-phenoxido compound like that of our dioxido compound. So, in the dioxo compound what we have seen just now, that which is hexacoordinated and two cis positions are occupied by two oxygen atoms of the dioxo groups. Similarly, here one of the group is occupied by this oxo function, which is the incoming oxo group from the trimethyl amine N oxide, and this particular phenoxido group is little bit go for some adjustment. So, coordination environment adjustment is taking place, and which is now occupying the transposition of this sulfur. So, transposition of this sulfur. So, this oxygen is basically moved from here to there, while giving space for accommodating this oxido group which is coming from trimethyl amine N oxide. But when we go for the corresponding oxo transfer reagent, we can also go for some reactions where we can have the sulfide transfer reagent. So, which is nothing but another type of groups is the trisulfide type of molecule. So, which is trisulfides, the polysulfides are well known for providing sulfur as S2 minus. So, this is a trisulfide reagent for that based on benzyl thiol. So, this can very easily provide sulfide anion to the system, and interestingly we all know that the sulfide groups, when we use the sulfide groups as a reagent in group analysis in analytical chemistry, we all know that S2 minus when it is available, it can react with many metal salts in +2 oxidation state like iron, like copper, and they go for their corresponding precipitation as MS. Metal sulfides, metal chalcogenides are precipitated out from the medium, and group analysis we can go for that. But here what is happening, that if we just provide S2 minus on compound number 40, Whether we can take out this sulfur tungsten as tungsten sulfide is not possible, because tungsten already in plus 4 oxidation state. So, WH2 is also not forming through the reaction of this reagent. So, metal ion transfer or the corresponding metathesis reaction based on the removal of the tungsten from this chelating environment is not possible with the use of this sulfur transfer reagent. What is happening instead, like that of oxotransfer reaction, the same reaction is taking place. That means, the reactivity of sulfur as sulfide ion or oxygen as oxide anion, both are similar, because this particular position is occupied by sulfur, what was occupied by oxygen in compound number 41. So, again this reorganization of this phenoxide anion is taking place, and sulfur is simply sitting over there as making the sulfur double bond with that of our tungsten center. So, what we see that the electron transfer reactions are taking place on all these molybdenum containing different hydroxylases, where we have the cysteine residues are present near 2 iron sulfur centers. So, several techniques like Raman, Endor and other spectroscopic methods also provide good informations for the electronic structure of these active sites of these enzymes. So, whether we have a tungsten site or a molybdenum site, so we will just follow the different spectroscopic techniques to establish what are the different oxidation states, what are their corresponding coordination environment, and how these metal centers are reacting with all these different groups. So, to know the corresponding nature of these active sites, so electronic structure determination is very important, which can inform us about the physical structure of the metal center of the active site and the corresponding chemistry available on it with respect to the electron transfer, what redox reactivity we can see, and how the new groups are coming and attaching to the metal center for ligand substitution or ligand addition reaction. So, for all these reactions based on the molybdenum and tungsten containing enzymes, the different spectroscopic methods are therefore very much useful to know the corresponding chemistry which is being catalyzed by these metal centers. So, this particular one can also be very nicely established in a very recent work which has been just published, where this diethylene group of molecules can be changed to that of your corresponding group of molecules where carboxy methoxy substitution. So, what should be the effect of this COOMe group with respect to the CN group? So, what we just change here, this one change for the ligand system is that we have the dithiol unit on in backbone, double bond backbone, and malonitrile dithiol we have checked earlier for the different model compounds. So, these can be compared with other substituted version, which is the corresponding ester function instead of the cyanide function, which is COOMe. How these groups are basically reacting to give the corresponding model compounds. So, the carboxy methoxy substituted dithionyl ligand, which is abbreviated as LCOMe. COMe is the substitution for the cyanide function, and these also very nicely give both monoxo as well as the dioxo compound, and these synthetic compounds can also be studied for their corresponding properties related to their structure, their spectroscopic signatures, and the different properties and reactivity related to the different tungsten enzymes, because these can also be studied for their corresponding molybdenum enzymes. And systematic study like that of our previous system can also be studied here also for the monoxo compound in plus 4 oxidation state and the dioxo compound in plus 6 oxidation state. But only thing why these ligand modifications we are doing, that the electronic structure on these ligands are different, and these can donate more electron to the metal site, and E0 values would therefore be modified, and how the more electron push from the ligand side, which is not possible when we study the biological counterpart of this ligand, the molybdoterine or the tungstoterine units, which cannot be modified, but for the synthetic molecules we can modify the ligand backbone, and we see how the environment for the electronic structure change can give rise to the other type of reactivity pattern on these centers. So, this particular case, that means when we get for the corresponding monoxo and dioxo compounds, so this ligand LCOMe can also stabilize this corresponding one as the corresponding oxo compound, the dioxo compound, and one is also important is the corresponding hybrid one, the oxosulfido species. Then other selanol, also selanol can also go for this oxygen transfer to this center, and this oxoselanol species can also be formed over there. So, addition and the electron transfer reactions based on these the different monodentate ligands, some is forming double bond and some are forming single bond, can give the exact geometry and electronic structure of these complexes, because theoretically we can also calculate the corresponding electronic structure of these complex, how the electronic structure can be useful for different enzymatic reactions that can be studied with these model compounds. Okay, thank you.